Hey, this is Jonathan with MarketplaceGOLD, and I'm going to be reading the Ethereum white paper here, and I invite you to listen along. I'm going to be adding some commentary and analysis to this reading. I hope you don't mind, along with some jokes, just to keep it amusing. I welcome your comments, feedback, upvotes, and of course, praise of my jokes in the comments below. And this white paper is long, so I have done drugs, well, more specifically, smart drugs, so that I can get through and deliver to you the eye-watering technical language of this. I hope that my delivery and my rapier wit keeps you awake throughout. You're going to want to check out MarketplaceGOLD, which is my geo directory of businesses, large and small, accepting Ethereum and other cryptocurrencies. Below, wherever you're watching this, I have a page linked, a nice directory page linked that lists all of the businesses out there accepting Ethereum. You might appreciate that this reading is not punctuated with annoying ads. If so, use MarketplaceGOLD to find vendors offering what you might want or need and pay with crypto with them. My website is not a middleman to transactions. Don't worry, I don't want your money. My website is just a place to find people to deal with. And if you're an entrepreneur, freelancer, or a business manager of some kind of organization accepting cryptocurrency, you'll want to take about 10 minutes to go and add a listing to MarketplaceGOLD. I've also got a link for that below. That listing is free to add and will remain so. And you can, of course, specify which cryptos you accept as a business, and then you'll be searchable by that. I think it's going to be something that can open up a new window of opportunity to really any business. And this listing, this reading of the Ethereum white paper is long. It is a thorough white paper. But if you really do want to understand Ethereum, I'd urge you to listen to the whole thing and pay attention to it. For the people who do that, I'm going to give you a little reward. I will send you a bit of Ethereum or maybe some other cryptocurrency if you send me an email or a message privately via social media with a special silly word. I'm going to be dropping a special silly word at some point during this recording. It's going to be a secret. Don't share it with anybody. Don't drop it in the comments, or else I can't. That would destroy the point of all this. But listen carefully. I'm going to drop a silly word and then just contact me and I'll send you a bit of crypto, just so I know who is paying attention. Well, let's dive into the Ethereum white paper. The Ethereum white paper. This introductory paper was originally published in 2013 by Vitalik Buterin, the founder of Ethereum, before the project's launch in 2015. Wow, 2013. That's a blast from the past, isn't it? Just think, what kind of cell phone did you have in 2013? I think I had a Windows phone. Boy, that was a different world, wasn't it? Anyways, it's worth noting that Ethereum, like many community-driven open source software projects, has evolved since its initial inception. While several years old, we maintain this paper because it continues to serve as a useful reference and an accurate representation of Ethereum and its vision. To learn about the latest developments of Ethereum and how changes to the protocol are made, we recommend this guide, and they link to it. First of all, a next-generation smart contract and decentralized application platform. I think that is the subtitle of the white paper. Satoshi Nakamoto's development of Bitcoin in 2009 has often been hailed as a radical development in money and currency, being the first example of a digital asset which simultaneously has no backing or intrinsic value and no centralized issuer or controller. However, another arguably more important part of the Bitcoin experiment is the underlying blockchain technology as a tool of distributed consensus. And attention is rapidly starting to shift to this and to this other aspect of Bitcoin. Commonly cited alternative applications of blockchain technology include using on-chain digital assets to represent custom currencies and financial instruments, colored coins. The ownership of an underlying physical device, smart property, now fungible assets such as domain names, as well as more complex applications, involve having digital assets being directly controlled by a piece of code implementing arbitrary rules, aka smart contracts, or even blockchain-based decentralized autonomous organizations, DAOs. And that is a cool acronym that they came up with that just harkens to Eastern spirituality. I think, aren't we all very, very, very spiritual? Crypto heads. Yes, we are. What Ethereum intends to provide is a blockchain with a built-in, fully fledged, Turing-complete programming language that can be used to create contracts that can be used to encode arbitrary state transition functions, allowing users to create any of the systems described above, as well as many others that we have not yet imagined, simply by writing up the logic in a few lines of code. Introduction to Bitcoin and existing concepts. First of all, history. The concept of decentralized digital currency, as well as alternative applications like property registries, has been around for decades. The anonymous e-cash protocols of the 1980s and the 1990s, mostly reliant on a cryptographic primitive known as Chumian binding, there's your phrase of the day, provided a currency with a high degree of privacy. But the protocols largely failed to gain traction because of their reliance on a centralized intermediary. And we don't like centralized intermediaries, do we? In 1998, and try to think back to 1998, boy, that was a year that you didn't even have a cell phone. Life was strange. You'd wander about in neighborhoods just looking for people to make friends with. or at least I did. Anyways, back in 1998, Wei Dai's B Money became, that is not a hip-hop album, but that is in fact a creation. I'll share more. B Money became the first proposal to introduce the idea of creating money through solving computational puzzles as well as decentralized consensus. But the proposal was scant on details as to how decentralized consensus could actually be implemented. In 2005, Hal Finney introduced a concept of reusable proofs of work, a system which uses ideas from B Money together with Adam Back's computationally difficult hash-cash puzzles to create a concept for a cryptocurrency, but once again fell short of the ideal by relying on trusted computing as a backend. In 2009, a decentralized currency was for the first time implemented in practice by the man of mystery himself, Satoshi Nakamoto, combining established primitives for managing ownership through public key cryptography with a consensus algorithm for keeping track of who owns coins, known as proof of work. Established primitives. Boy, that sounds like that could be a keto kind of supplement, perhaps, maybe. I don't know. I'll try it. I'll try selling it for Ethereum. We'll see if anybody buys it. Moving on. The mechanism behind proof of work was a breakthrough in the space because it simultaneously solved two problems. First, it provided a simple and moderately effective consensus algorithm, allowing nodes in the network to collectively agree on a set of canonical updates to the state of the Bitcoin ledger. Second, it provided a mechanism for allowing free entry into the consensus process, solving the political problem of deciding who gets to influence the consensus. And boy, in the year 2021, all we have is political problems. Moving on, while simultaneously preventing Sybil attacks, it does this by substituting a formal barrier to participation, such as the requirement to be registered as a unique entity on a particular list with an economic barrier. The weight of a single node in the consensus voting process is directly proportional to the computing power that the node brings. Since then, an alternative approach has been proposed called proof of stake, calculating the weight of a node as being proportional to its currency holdings and not computational resources. The discussion of the relative merits of the two approaches is beyond the scope of this paper, but it should be noted that both approaches can be used to serve as the backbone of a currency. Here is a blog post from Vitalik Buterin, the founder of Ethereum, entitled simply Ethereum Prehistory. Boy, Vitalik needs to learn how to write more attention-grabbing blog titles than that. That's not going to get a whole lot of clicks. Okay, however, on a more serious note, he writes, Bitcoin as a state transition system. From a technical standpoint, The ledger of a cryptocurrency such as Bitcoin can be thought of as a state transition system where there is a state consisting of the ownership status of all existing Bitcoins and a state transition function that takes a state and a transaction and outputs a new state, which is the result. I'm following you, Vitalik. In a standard banking system, for example, the state is a balance sheet. A transaction is a request to move $X from A to B. And the state transition function reduces the value in A's account by $X and increases the value in B's account by $X. If A's account has less than $X in the first place, the state transition function returns an error. Hence, one can formally define. And we've got some code there. Check it out in the white paper. I'll link to it below wherever you're listening to this podcast. The state in Bitcoin is the collection of all coins. Technically, unspent transaction outputs, or UTXO. Oh, fantastic. Acronyms. I was really hoping that there was going to be a lot of acronyms for us to keep track of here. That have been mined and not yet spent, with each UTXO having a denomination and an owner, defined by a 20-byte address, which is essentially a cryptographic public key. A transaction contains one or more inputs, with each input containing a reference to an existing UTXO and a cryptographic signature produced by the private key associated with the owner's address, and one or more outputs, with each output containing a new UTXO to be added to the state. And a state transition function can be defined roughly as follows. Let's jump past a few of these equations towards conclusions. The first half of the first step prevents transaction senders from spending coins that do not exist. The second half of the first step prevents transaction senders from spending other people's coins. And the second step enforces conservation of value. And if there's anything that I'm about, it is conservation of value. I am a right-wing, right-thinking, conservationist of value kind of guy. In order to use this for payment, the protocol is as follows. Suppose Alice wants to send 11.7 BTC to Bob. Boy, Alice is a good friend. I wish I had friends like Alice. First, Alice will look for a set of available UTXO that she totals up to at least 11.7 BTC. Realistically, Alice will not be able to get exactly 11.7 BTC. Say that the smallest that she can get is 6 plus 4 plus 2 equals 12. She then creates a transaction with those 3 inputs and 2 outputs. The first output will be 11.7 BTC with Bob's address as the owner. And the second output will be the remaining 0.3 BTC change, with the owner being Alice herself. And boy, Bob should really be there to help Alice next time she's moving. Bob should be the first guy that she calls up and says, "Hey, buddy old pal Bob, I need your help moving an old couch." And he should be there. You know, that's the kind of friend we all want, so that's the kind of friend we should try to be. Moving on, Let's talk about mining. And we've got kind of a cool diagram of the Ethereum blocks. If we had access to a trustworthy centralized service, this system would be trivial to implement. It could simply be coded exactly as described using a centralized server's hard drive to keep track of the state. However, with Bitcoin, we are trying to build a decentralized currency system. So we will need to combine the state transition system with a consensus system in order to ensure that everyone agrees on the order of transactions. Bitcoin's decentralized consensus process requires nodes in the network to continuously attempt to produce packages of transactions called blocks. The network is intended to produce roughly one block every 10 minutes, with each block containing a timestamp, a nonce, a reference to a hash of the previous block, and a list of all of the transactions that have taken place since the previous block. Over time, this creates a persistent, ever-growing blockchain that constantly updates to represent the latest state of the Bitcoin ledger. The algorithm for checking if a block is valid expressed in this paradigm is as follows. 1, check if the previous block referenced by the block exists and is valid. 2, check that the timestamp of the block is greater than that of the previous block and less than 2 hours into the future. 3, check that the proof of work on the block is valid. 5, let SO be the state of the previous block. Suppose that TX is the block's transaction list with N transactions. And 6, returns true and register S number 5 as the state at the end of the block. Whew, I powered right through that, didn't I? I'm on sufficient 12,3,7-trimethylxanthine to do so. 12,3,7-trimethylxanthine is the chemical name for caffeine, of course. Essentially, each transaction in the block must provide a valid state transition from what was the canonical state before the transaction was executed to some new state. Note that the state is not encoded in the block in any way. It is purely an abstraction to be remembered by the validating node and can only be securely computed for any block by starting from the genesis state and sequentially applying every transaction in every block. Additionally, note that the order in which the miner includes transactions into the block matters. If there are 2 transactions, A and B, in a block, such that B spends a UTXO created by A, then the block will be valid if A comes before B, but not otherwise. The one validity condition present in the above list that is not found in other systems is the requirement for proof of work. The precise condition is that the double SHA-256 hash of every block, treated as a 256-bit number, must be less than a dynamically adjusted target, which, as of the time of this writing, is approximately 2 to the 187th power. Wow, that's a lot of zeros. Just try to imagine all those zeros. The purpose of this is to make the block creation computationally hard. thereby preventing Sybil attackers from remaking the entire blockchain in their favor, because SHA-256 is designed to be completely unpredictable pseudodom. Oh my gosh, this is a new word that I have never read before. Pseudo-random. Completely unpredictable pseudo-random function. Pseudo-random. Okay. That can be a word. That's two words that I know of, and we just put them together, and it's a new word, and it's kind of a cool new word, right? Pseudo-random. The only way to create a valid block is simply trial and error, repeatedly incrementing the nonce and seeing if the new hash matches. At the current target of 2 to the 187th power, the network must make an average of 2 to the 69th power tries before a valid block is found. In general, the target is recalibrated by the network every 2016 blocks so that on average, a new block is produced by some node in the network every 10 minutes. In order to compensate the miners for this computational work, the miner of every block is entitled to include a transaction giving themselves 12.5 BTC out of nowhere. Boy, I would sure like to give myself 12.5 BTC out of nowhere. Just let me know, Vitalik, where I can sign up for that. Additionally, if any transaction has a higher total denomination in its inputs than in its outputs, the difference also goes to the miner as a transaction fee. Incidentally, this is also the only mechanism by which BTC are issued. The Genesis state contained no coins at all. In order to better understand the purpose of mining, let us examine what happens in the event of a malicious attacker. Since Bitcoin's underlying cryptography is known to be secure, the attacker will target the one part of the Bitcoin system that is not protected by cryptography directly: the order of transactions. The attacker's strategy is simple. Send 100 BTC to a merchant in exchange for some product, preferably a rapid delivery digital good. Wait for the delivery of the product. Produce another transaction sending the same 100 BTC to himself. Try to convince the network that his transaction was to himself was the one that came first. Interesting. So is that the way it could be cheated? Let's read on. Once step 1 has taken place, after a few minutes, some miner will include the transaction in a block, say block number 270. After about 1 hour, 5 more blocks will have been added to the chain after that block, with each of those blocks indirectly pointing to the transaction and thus confirming it. At this point, the merchant will accept the payment as finalized and deliver the product. Since we are assuming this is a digital good, delivery is instant. Now the attacker creates another transaction sending the 100 BTC to himself. If the attacker simply releases it into the wild, the transaction will not be processed. Miners will attempt to apply and notice that TX consumes a UTXO, which is no longer in the state. So instead, the attacker creates a fork of the blockchain, starting by mining another version of block 270, pointing to the same block 269 as a parent, but with the new transaction in place of the old one. Because the block data is different, this requires redoing proof of work. Furthermore, the attacker's new version of block 270 has a different hash. So the original blocks 271 to 275 do not point to it. Thus, the original chain and the attacker's new chain are completely separate. The rule is that in a fork, the longest chain is taken to be the truth. And so legitimate miners will work on the 275 chain, while the attacker alone is working on the 270 chain. In order for the attacker to make his blockchain the longest, he would need to have more computational power than the rest of the network combined in order to catch up. Hence, we call this a 51% attack. You've probably heard of that before. We don't want 51% attacks, do we? Next, let's move on to Merkle trees. I wonder if the Merkle trees lose their leaves during the winter time. Okay, left. It suffices to present only a small number of nodes in a Merkle tree to give a proof of the validity of the branch. Right. Any attempt to change any part of the Merkle tree will eventually lead to an inconsistency somewhere up the chain. An important scalability feature of Bitcoin is that the block is stored in a multi-level data structure. The hash of a block is actually only the hash of the block header, a roughly 200 byte piece of data that contains the timestamp, nonce, previous block hash, and the root hash of a data structure called the Merkle tree, storing all transactions in the node. A Merkle tree is a type of binary tree composed of a set of nodes with a large number of leaf nodes at the bottom of the tree containing the underlying data. A set of intermediate nodes where each node is the hash of its two children. And finally, a single root node also formed from the hash of its two children, representing the top of the tree. The purpose of the Merkle tree is to allow the data in a block to be delivered piecemeal. A node can be downloaded only the header of a block from one source, the small part of the tree relevant to them from another source, and still be assured that all of the data is correct. The reason why this works is that hashes propagate upward. If a malicious user attempts to swap in a fake transaction into the bottom of a Merkle tree, this change will cause a change in the node above, and then a change in the node above that, finally changing the root of the tree and therefore the hash of the block, causing the protocol to register it as a completely different block, almost certainly with an invalid proof of work. The Merkle tree protocol is arguably essential to long-term sustainability. A full node in the Bitcoin network, one that stores and processes the entirety of every block, takes up about 15 gigabytes of disk space in the Bitcoin network as of April 2014, and is growing by over a gigabyte per month. Apparently, this is viable for some desktop computers and not phones. And later on in the future, only businesses and hobbyists will be able to participate. A protocol known as Simplified Payment Verification, SPV, allows for another class of nodes to exist called light nodes, which download the block headers, verify the proof of work on the block headers, and then download only the branches associated with transactions that are relevant to them. This allows light nodes to determine with a strong guarantee of security what the problem of any Bitcoin transaction and their current balance is, while downloading only a very small portion of the entire blockchain. Next section, alternative blockchain applications. The idea of taking the underlying blockchain idea and applying it to other concepts also has a long history. In 1998, Nick Szabo came out with the concept of secure property titles with owner authority, a document describing how new advances in replicated database technology will allow for a blockchain-based system for storing a registry of who owns what land, creating an elaborate framework, including concepts such as homesteading, adverse possession, and Georgian land tax. I wonder if they're talking about Georgia in the South in America, or if they're talking about Georgia on the other side of the Black Sea from where I live, or if they're talking about Georgian monks. I can only Google this and I would find out. Anyways, however, there was unfortunately no effective replicated database system available at the time, and so the protocol was never implemented in practice. After 2009, however, once Bitcoin's decentralized consensus was developed, a number of alternative applications rapidly began to emerge. A few of them. Namecoin, created in 2010, Namecoin is best described as a decentralized name registration database. In decentralized protocols like Tor, Bitcoin, and BitMessage, there needs to be some way of identifying accounts so that other people can interact with them. But in all existing solutions, the only kind of identifier available is a pseudo-random hash, like this big long hash that he came up with. Ideally, one would like to be able to have an account with a name like George. However, the problem is that if one person can create an account named George, then someone else can use the name process to register George for themselves as well and impersonate them. Oh, George, are you really George? The only solution is a first-to-file paradigm, where the first registerer succeeds and the second fails, a problem perfectly suited for the Bitcoin consensus protocol. Namecoin is the oldest and most successful implementation of a name registration using such an idea. And that just makes me curious. Namecoin is indeed a thing. It is indeed a cryptocurrency. I didn't know about that. Well, that's why I'm reading white papers, as I'm trying to learn things. Okay, next. colored coins. Are you a colored? Well, I don't have anything against the coloreds. I'm perfectly fine with the coloreds. I'm a forward-thinking, progressive type of Southern gentleman. The coloreds are fine by me. Okay, about the colored coins. The purpose of colored coins is to serve as a protocol to allow people to create their own digital currencies, or in the important trivial case of a currency with one unit, digital tokens on the Bitcoin blockchain. In the colored coins protocol, one issues a new currency by publicly assigning a color to a specific Bitcoin UTXO, and the protocol recursively defines the color of other UTXO to be the same as the color of the inputs that the transaction creating them spent. Some special rules apply in the case of mixed colored inputs. This allows users to maintain wallets by containing only UTXO of a specific color and send them around, much like regular Bitcoins, backtracking through the blockchain to determine the color of any UTXO that they receive. Meta coins. The idea behind a meta coin is to have a protocol that lives on top of Bitcoin, using Bitcoin transactions to store metacoin transactions, but having a different state transition function apply because the metacoin protocol cannot prevent invalid metacoin transactions from appearing in the Bitcoin blockchain. A rule is added that if apply returns an error, the protocol defaults to apply. This provides an easy mechanism for creating an arbitrary cryptocurrency protocol, potentially with advanced features that cannot be implemented inside of Bitcoin itself, but with a very low development cost, since the complexities of mining and networking are already handled by the Bitcoin protocol. Metacoins have been used to implement some cases of financial contracts, name registration, and decentralized exchange. Thus, in general, there are two approaches toward building a consensus protocol: building an independent network and building a protocol on top of Bitcoin. The former approach, while reasonably successful in the case of applications like Namecoin, is difficult to implement. Each individual implementation needs to bootstrap an independent blockchain, as well as building and testing all the necessary state transition and networking code. Additionally, we predict that the set of applications for decentralized consensus technology will follow a power law distribution where the vast number of applications would be too small to warrant their own blockchain. And we note that there exist large classes of decentralized applications, particularly decentralized autonomous organizations, aka DAOs, that need to interact with each other. The Bitcoin-based approach, on the other hand, has the flaw that it does not inherit the simplified payment verification features of Bitcoin. SPV works for Bitcoin because it can use blockchain depth as a proxy for validity. At some point, once the ancestors of a transaction go far enough back, it is easy to say that they were legitimately part of the state. Blockchain-based meta protocols, on the other hand, cannot focus the blockchain not to include transactions that are not valid within the context of their own protocols. Hence, a fully secure SPV meta protocol implementation would need to backward scan all the way to the beginning of the blockchain protocol to determine whether or not certain transactions are valid. Currently, all light implementations of Bitcoin-based meta protocols rely on a trusted server to provide the data, arguably a highly suboptimal result, especially when one of the primary purposes of a cryptocurrency is to eliminate the need for trust. Amen, brother. I couldn't agree with you more on that account. Next section, scripting. Even without any extensions, the Bitcoin protocol actually does facilitate a weak version of a concept of smart contracts. Interesting. UTXO in Bitcoin can be owned not just by a public key, but also by a more complicated script expressed in a simple stack-based programming language. In this paradigm, a transaction spending that UTXO must provide data that satisfies the script. Indeed, even with the basic public key ownership mechanism is implemented via a script, the script takes an elliptical curve signature as input, verifies it against the transaction and the address that owns the UTXO, and returns 1 if the verification is successful, and 0 otherwise. Other more complicated scripts exist for various additional use cases. For example, one can construct a script that requires signatures from 2 out of a given 3 private keys to validate multisig, a setup useful for corporate accounts, secure savings accounts, and some merchant escrow situations. Scripts can also be used to pay bounties for the solutions to computational problems. And one can even construct a script that says something like, this Bitcoin UTXO is yours if you can provide an SPV proof that you sent a Dogecoin transaction of this denomination to me, essentially allowing decentralized cross-cryptocurrency exchange. Oh yeah, that's what we want. The future beckons, baby. However, the scripting language as implemented in Bitcoin has several important limitations. Lack of Turing completeness. This is to say, while there is a large subset of computation that the Bitcoin scripting language supports, it does not nearly support everything. The main category that is missing is loops. This is done to avoid infinite loops during transaction verification. Theoretically, it is a surmountable obstacle for script programmers, since any loop can be simulated by simply repeating the underlying code many times with an if statement. But it does lead to scripts that are very space inefficient. For example, implementing an alternative elliptical curve signature algorithm would likely require 256 repeated multi-application rounds, all individually included in the code. Value blindness. This is what they teach you in college while you're doing all the drugs. Value blindness. There is no way for a UTXO script to provide fine-grained control over the amount that can be withdrawn. For example, one powerful use case of an Oracle contract would be a hedging contract where A and B put in $1,000 worth of BTC, and another 30 days, the script sends $1,000 worth of BTC to A and the rest to B. This would require an oracle to determine the value of one BTC in USD. But then it is a massive improvement in terms of trust and infrastructure requirement over the fully centralized solutions that are available now. However, because UTXO are all or nothing, the only way to achieve this is through the very inefficient hack of having many UTXO of varying denominations and having zero pick which UTXO to send A and which to send to B. Lack of state. A UTXO can either be spent or unspent. There is no opportunity for multi-stage contracts or scripts which keep any other internal state beyond that. This makes it hard to make multi-stage options contracts, decentralized exchange offers, or two-stage cryptographic commitment protocols necessary for secure computational bounties. It also means that UTXO can be used to build simple one-off contracts and not more complex stateful contracts such as decentralized organizations, and makes meta protocols difficult to implement. Binary state combined with value blindedness also mean that another important application, withdrawal limits, is impossible. Blockchain blindedness. UTXO are blind to blockchain data such as the nonce, the timestamp, and previous block hashes. This severely limits applications in gambling and several other categories by depriving the scripting language of a potentially valuable source of randomness. Thus, we see three approaches to building advanced applications on top of cryptocurrency: building a new blockchain, using scripting on top of Bitcoin, and building a meta protocol on top of Bitcoin. Building a new blockchain allows for unlimited freedom in building a feature set, and at the cost of development time, bootstrapping effort and security. Using scripting is easy to implement and standardize, but is very limited in its capabilities, and meta protocols, while easy, suffer from faults in scalability. With Ethereum, we intend to build an alternative framework that provides even larger gains in ease of development, as well as even stronger light client properties, while at the same time allowing applications to share an economic environment and blockchain security. Next section, Ethereum. The intent of Ethereum is to create an alternative protocol for building decentralized applications, providing a different set of trade-offs that we believe will be very useful for a large class of decentralized applications, with particular emphasis on situations where rapid development time, security for small and rarely used applications, and the ability of different applications to efficiently interact are important. Ethereum does this by building what is essentially the ultimate abstract foundational layer. Dun, 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 dun. A blockchain with a built-in Turing-complete programming language, allowing anyone to write smart contracts and decentralized applications where they can create their own arbitrary rules for ownership. Like, everybody must make a compliment of my hair if they want to come to the party. That's the kind of arbitrary rule for ownership that I'm about. Transaction formats and state transition functions. A bare bones version of Namecoin can be written in 2 lines of code, and other protocols like currencies and reputation systems can be built in under 20 lines of code, under 20 minutes. I'm not sure. Smart contracts, cryptographic boxes that contain value and only unlock it if certain conditions are met, can also be built on top of the platform with vastly more power than that offered by Bitcoin scripting because of the added powers of Turing completeness, value awareness, blockchain awareness, and state. Philosophy. Oh yes, this is the part I think I'm going to enjoy. I'm all about philosophy. Check out some of the other philosophically minded sort of podcasts that you can find on this show. The design behind Ethereum is intended to follow the following principles. Number 1, simplicity. The Ethereum protocol should be as simple as possible, even at the cost of some data storage or time efficiency. An average programmer should ideally be able to follow and implement the entire specification so as to fully realize the unprecedented democratizing potential that cryptocurrency brings, and further the vision of Ethereum as a protocol that is open to all. Any optimization that adds complexity should not be included unless that optimization provides very substantial benefit. Second, universality. A fundamental part of Ethereum's design philosophy is that Ethereum does not have features. Instead, Ethereum provides an internal Turing-complete scripting language, which a programmer can use to construct any smart contract or transaction type that can be mathematically defined. Want to invent your own financial derivative? Oh, yes, I do. Yes, I do. I want to be like those guys in Wall Street back then in 2008, messing around, fooling around with their own financial derivatives. That sounds like a jolly good time to me. Well, with Ethereum, you can. Want to make your own currency? Set it up as an Ethereum contract. Want to set up a full-scale daemon or Skynet, like in the Terminator franchise? You may need to have a few thousand interlocking contracts and be sure to feed them generously so they don't bite your hand to do that. But nothing is stopping you with Ethereum at your fingertips. Hey, this is arousing some devious instincts of mine. Number 3, thirdly, the parts of the Ethereum protocol should be designed to be as modular and separable as possible. Over the course of development, our goal is to create a program where if one was to make a small protocol modification in one place, the application stack would continue to function without any further modification. Innovations such as ETH hash, like ETH hash, and RLP should be and are implemented as separate, feature-complete libraries. This is so that even though they are used in Ethereum, even if Ethereum does not require certain features, such features are still usable in other protocols as well. Ethereum development should be maximally done so as to benefit the entire cryptocurrency ecosystem, not just itself. Fourthly, agility. Details of the Ethereum protocol are not set in stone, although we will be extremely judicious about making modifications to high-level constructs. For instance, with the sharding roadmap, abstracting execution with only data availability enshrined in consensus. Computational tests later on in the development process may lead us to discover that certain modifications, for example, to the protocol architecture or to the Ethereum virtual machine, the EVM, will substantially improve scalability or security. If any such opportunities are found, we will exploit them. And 5, non-discrimination and non-censorship. The protocol should not attempt to actively restrict or prevent specific categories of usage. All regulatory mechanisms in the protocol should be designed to directly regulate the harm and not attempt to oppose specific undesirable applications. A programmer can even run an infinite loop script on top of Ethereum for as long as they are willing to keep paying the per computational step transaction fee. Okay, so this is similar to Bitcoin, a system beautifully designed with human nature in mind, saying, look, you can do what you want. You can use this system as you please. Just pay for what you take in the form of the Ethereum gas fees, right? Okay, moving on. We'll talk about Ethereum accounts. In Ethereum, the state is made up of objects called accounts, with each account having a 20-byte address and state transitions being direct transfers of value and information between accounts. An Ethereum account contains 4 fields: a nonce, a counter used to make sure that each transaction can only be processed once. And I want to look this up again. What the heck is a nonce? In the Urban Dictionary, there's some funny definitions for it. I thought there was a technical. Aha, here it is. Here's the technical. It's an abbreviation. So it stands for number only used once. A nonce. A number only used once. That's right. Like in the call sign of James Bond, 7 would be the nonce. It's a number only used once, 007, right? Okay, moving on. The account's current Ether balance, the account's contract code, if present, and the account's storage, empty by default. Ether is the main internal crypto Okay, Ether is the main internal crypto fuel of Ethereum and is used to pay transaction fees. Okay, so Ethereum is kind of like the operating system, if you were. I've heard Ethereum described as a planetary scale computer. So Ether is not just an abbreviation of Ethereum. Ether is the fuel. Ether is the currency itself. In general, there are two types of accounts. Externally owned accounts controlled by private keys and contract accounts controlled by their contract code. An externally owned account and has no code, and one can send messages from an externally owned account by creating and signing a transaction. In a contract account, every time the contract account receives a message, its code activates, allowing it to read and write to internal storage and send other messages or create contracts in turn. Note that contracts in Ethereum should not be seen as something that should be fulfilled or compelled with. Rather, they are more like autonomous agents that live inside of the Ethereum execution environment, always executing a specific type of code when poked by a message or transaction, and having direct control over their own Ether balance and their own key value store to keep track of persistent variables. Okay, the first part of that very long sentence is pretty important. I'll actually repeat it for you. Note that contracts in Ethereum should not be seen as something that should be fulfilled or compelled with or complied with, kind of the same way that contracts in the real world might be fulfilled or that they might be demanded by, say, a court or a judge to be complied with. Rather, Ethereum contracts are more like autonomous agents that live inside of the Ethereum execution environment. So Ethereum smart contracts are, shall we say, non-negotiable, which is what's kind of enabling the trustless philosophy that underlies the whole cryptocurrency thing, right? Moving forward, let's talk about messages and transactions. The term transaction is used in Ethereum to refer to the signed data package that stores a message to be sent from an externally owned account. Transactions contain the recipient of the message, a signature identifying the sender, the amount of Ether to transfer from the sender to the recipient, or an optional data field. At start gas value, which is, the value that I'm at after having some beans for dinner, representing the maximum number of computational steps the transaction execution is allowed to take. A gas price value representing the fee the sender pays per computational step after having too many beans in a spicy stew. Just kidding, that part I added myself. The first three are standard fields expected in any cryptocurrency. The data field has no function by default, but the virtual machine has an upcode which a contract can use to access the data. As an example use case, if a contract is functioning as an on-chain domain registration service, then it may wish to interpret the data being passed to it as containing two fields. The first field being a domain to register, and the second field being the IP address to register it to. The contract would read these values from the message data and appropriately place them in storage. The start gas and the gas price fields are crucial for Ethereum's anti-denial of service model. In order to prevent accidental or hostile infinite loops or other computational wastage in code, each transaction is required to set a limit to how many computational steps of code execution it can use. The fundamental unit of computation is gas. Usually a computational step costs 1 gas, but some operations cost higher amounts of gas because they are more computationally expensive, or increase the amount of data that must be stored as part of the state. There's also a fee of 5 gas for every byte in the transaction data. The intent of the fee system is to require an attacker to pay proportionately for every resource that they consume, including computation, bandwidth, and storage. Hence, any transaction that leads to the network consuming a greater amount of any of these resources must have a gas fee roughly proportional to the increment. Moving on, messages. Contracts have the ability to send messages to other contracts. Messages are virtual objects that are never serialized and only exist in the Ethereum execution environment. A message contains the sender of the message, that's implicit, the recipient of the message, amount of either ether to transfer alongside the message, an optional data field, that's where you can put in your flirtatious kitty cat emoticon, and finally a start gas value. Essentially, a message is like a transaction, except it is produced by a contract and not an external actor. A message is produced when a contract currently executing code executes the call op code, which produces and executes a message. Like a transaction, a message leads to the recipient account running its code. Thus, contracts can have relationships with other contracts in exactly the same way that external actors can. And this talk of external actors has just got me thinking about, like, maybe you have a Hollywood movie and you've got some extras that are appearing in the different scenes. You know, the extras are the external actors, and maybe they are like they're like the zombies. You know, in a zombie movie, you got the movie star with the great hair, and then you've got the chick that needs to be saved every 15 minutes, and then you've got the hordes of zombies, which are played by, you know, obviously not the most talented actors. And so I'm imagining the talentless actors are just, you know, having relationships with each other and giving each other STDs there in their trailers of the movie, and then sometimes also giving STDs to the movie star also, because the movie star is also banging the nobodies. So that's what I'm thinking. That's the metaphor that's coming together in my head. Let me know if that makes a lot of sense. Let me know if you're picking up what I'm laying down. Moving on, note that the gas allowance assigned by a transaction or contract applies to the total gas consumed by that transaction and all executions. For example, if an external actor sends a transaction to B with 1,000 gas, and B consumes 600 gas before sending a message to C, and the internal execution of C consumes 300 gas before returning, then B can spend another 100 gas before running out of gas. And then you gotta get to walking, right? That's the way it goes. Ethereum state transition function. The Ethereum state transition function apply STX5 can be defined as follows. Check if the transaction is well formed, has the right number of values, the signature is valid, and the nonce, the number used only once, matches the nonce in the sender's account. If not, return an error. Calculate the transaction fee as start gas times gas price and determine the sending address from the signature. Subtract the fee from the sender's account balance and increment the sender's nonce. If there is not enough balance to spend, return an error. Initialize gas equals start gas and take off a certain quantity of gas per byte to pay for the bytes in the transaction. Transfer the transaction value from the sender's account to the receiving account. If the receiving account does not exist, create it. If the receiving account is a contract, run the contract's code either to completion or until the execution runs out of gas. If the value transfer failed because the sender did not have enough money or the code execution ran out of gas, revert all state changes except the payment of the fees and add the fees to the miner's account. Otherwise, refund the fees for all remaining gas to the sender and send all fees paid for the gas consumed to the miner. Whew. Boy, some of this stuff I just want to power through. I want to speed read like that. There was a rapper. What was the name of that rapper that could rap really, really fast? I forget. But I want to be like that guy in some sections of this white paper. Sorry. Go and read the white paper. Control F in the white paper to find what you want to track down if there's something that I speed read through. Note that in reality, the contract code is written in the low-level EVM code. This example is written in Serpent, one of our high-level languages. That sounds like a badass language. Serpent? Fuck yeah. Do you speak Serpent? I do. For clarity, and can be compiled down to EVM code. Suppose that the contract storage starts off empty and a transaction is sent with 10 ether value, 2000 gas, 0.0001 ether gas price, and 64 bits of data, with bits 0 through 31 representing the number 2 and bytes 32 through 63 representing the string Charlie and process for the state transaction function in the case is as follows. 1. Check that the transaction is valid and well formed. 2. Check that the transaction sender has at least 2000 times 0.0001 equals 2 ether. If it is, then subtract 2 ether from the sender's account. And 3, initialize gas equals 2000, assuming the transaction is 170 bytes long and the byte fee is 5. Subtract 850 so that there is 1150 gas left. Subtract 10 more ether from the sender's account and add it to the contract account. Run the code. In this case, this is simple. It checks if the contract storage at index 2 is used, notices that it is not, and so it sets the storage at index 2 to the value Charlie. Suppose this takes 187 gas, so the remaining amount of gas is 1150 minus 187 equals 963. Add 963 times 001 and 0.0963 ether back to the sender's account and return the resulting state. If there was no contract at the receiving end of the transaction, then the total transaction fee would simply be equal to the provided gas price multiplied by the length of the transaction in bytes. And the data sent alongside the transaction would be irrelevant. Note that messages work equivalently to transactions in terms of reverts. If a message execution runs out of gas, then that message's execution and all other executions triggered by that execution revert, but parent executions do not need to revert. This means that it is safe for a contract to call another contract. As if A calls B with C gas, then A's execution is guaranteed to lose at most G gas. Finally, note that there is an upcode, create, that creates a contract. Its execution mechanics are generally similar to call, with the exception that the output of the execution determines the code of a newly created contract. Code execution. The code in Ethereum contracts is written in a low-level stack-based bytecode language, referred to as Ethereum Virtual Machine Code, or EVM code. The code consists of a series of bytes, where each byte represents an operation. In general, code execution is an infinite loop that consists of repeatedly carrying out the operation at the current program counter, which begins at 0, and then implementing the program counter by 1 until the end of the code is reached or an error or stop or return instruction is detected. The operations have access to 3 types of space in which to store data. The stack, a last in, first out container to which values can be pushed and popped. Memory, an infinitely expandable byte array. The contract's long-term storage, a key value store. Unlike stack and memory, which reset after computation ends, storage persists for the long term. The code can also access the value, sender, and data of the incoming message, as well as block headers and data. And the code can also return a byte array of data as an output. The formal execution model of EVM code is surprisingly simple. While Ethereum Virtual Machine is running, its full computational state can be defined by the tuple. That is a brand new word to me. Tuple, where where is the global state containing all accounts and includes balances and storages. At the start of every round of execution, the current instruction can be found by taking pth byte of code, or if and each instruction has its own definition in terms of how it affects the tuple. For example, add pops 2 items off the stack and pushes their sum, reduces gas by 1 and increments PC by 1. And store pops the 2 items off the stack and inserts the second item into the contract storage as the index specified by the first item. Although there are many ways to optimize Ethereum virtual machine execution via just-in-time compilation, a basic implementation of Ethereum can be done in a few hundred lines of code. Well, that's kind of interesting, isn't it? Now we're going to talk about blockchain and mining. The Ethereum blockchain is in many ways similar to the Bitcoin blockchain, although it does have some differences. The main difference between Ethereum and Bitcoin with regard to the blockchain architecture is that, unlike Bitcoin, which only contains a copy of the transaction list, Ethereum blocks contain a copy of both the transaction list and the most recent state. Aside from that, two other values, the block number and the difficulty, are also stored in the block. The basic block validation algorithm in Ethereum is as follows. 1. Check if the previous block reference exists and is valid. 2. Check that the timestamp of the block is greater than that of the reference previous block and less than 15 minutes into the future. 3. Check that the block number, difficulty, transaction root, uncle root, and gas limit, various low-level Ethereum specific concepts, are valid. 4. Check that the proof of work on the block is valid. 5. Let S0 be the state of the end of the previous block. 6. Let TX be the block transaction list with N transactions for all 1 of 0 and 1 set 5 S11 plus equals apply S1 TXI. If any application returns an error or if the total gas consumed in the block up until this point exceeds the gas limit, return an error. 7. Let S final be SN, but adding the block reward paid to the miner. 8. Check if the Merkle root for the state S final is equal to the final state provided in the block header. If it is, the block is valid. Otherwise, it's not valid, man. Whew. The approach may seem highly inefficient at first glance because it needs to store the entire state with each block. But in reality, efficiency should be compared to that of Bitcoin. The reason is that the state is stored in the tree structure. And after every block, only a small part of the tree needs to be changed. Thus, in general, between two adjacent blocks, the vast majority of the tree should be the same, and therefore the data can be stored once and referenced twice using pointers, for example, hashes of subtrees. A special kind of tree known as a Patricia tree is used to accomplish this, including a modification to the Merkle tree concept that allows for nodes to be inserted and deleted, and not just changed efficiently. Additionally, because all of the state information is part of the last block, there is no need to store the entire blockchain history. A strategy which, if it could be applied to Bitcoin, could be calculated to provide a 5 to 20x savings in space. A commonly asked question is where contract code is executed in terms of physical hardware. This has a simple answer. The process of executing contract code is part of the definition of the state transition function, which is part of the block validation algorithm. So if a transaction is added into block B, the code execution spawned by that transaction will be executed by all nodes now and in the future that download and validate block B. Okay. And we are going to move into the third part of the whole story now. The third part of the white paper is applications. You've heard so much about the applications of Ethereum. In general, there are 3 types of applications on top of Ethereum. The first category is financial applications, providing users with more powerful ways of managing and entering into contracts using their money. This includes sub-currencies, financial derivatives, hedging contracts, savings wallets, wills, and ultimately even some classes of full-scale employment contracts. The second category is semi-financial applications, where money is involved, but there is also a heavy non-monetary side to what is being done. A perfect example is self-reinforcing bounties for solutions to computational problems. Finally, there are applications such as online voting and decentralized governance that are not financial at all. And that kind of brings us to the crypto democracy concept that you've probably heard of, that maybe, one day we can do away with contentious and disputed elections because we'll have cryptocurrency transactions verifying things. Boy, that's a future that I dream of, but won't be holding my breath for. Next, token systems. On blockchain token systems have many applications ranging from sub-currencies representing assets such as USD or gold to company stocks, individual tokens representing smart property, secure unforgeable, or is that unforgettable coupons? I'm not sure. And even token systems with no ties to conventional value at all, used as point systems for incentivization. Token systems are surprisingly easy to implement in Ethereum. The key point is to understand that a currency or token system fundamentally is a database with one operation. Subtract X units from A and give X units to B with the provision that 1, A had at least X units before the transaction, and 2, the transaction is approved by A. All that it takes to implement a token system is to implement this logic into a contract. The basic code for implementing a token system in Serpent looks as follows. And we got a piece of computer code there. This is essentially a literal implementation of the banking system state transition function described further above in this document. A few extra lines of code need to be added to provide for the initial step of distributing the currency units in the first place, and a few other edge cases. And ideally, a function would be added to let other contracts query for the balance of an address. But that's all there is to it. Theoretically, Ethereum-based token systems acting as sub-currencies could potentially include another important feature that on-chain Bitcoin-based meta-currencies lack, which is the ability to pay transaction fees directly in that currency. The way this would be implemented is that the contract would maintain an Ether balance with which it would refund Ether used to pay fees to the sender. And it would refill this balance by collecting the internal currency units that it takes in fees and reselling them in a constant running auction. Users would thus need to activate their accounts with Ether. But once the Ether is there, it would be reusable because the contract would refund it each time. Okay, let's move on to financial derivatives and stable value currencies. Stable value currencies. Boy, that's something that I'm interested in. That's something that I've delved into quite a bit with the MarketplaceGOLD project. Financial derivatives are the most common application of a smart contract and one of the simplest to implement in code. The main challenge in implementing financial contracts is that the majority of them require reference to an external price ticker. For example, a very desirable application is a smart contract that hedges against the volatility of Ether or another cryptocurrency with respect to the US dollar. But doing this requires the contract to know what the value of ETH2 USD is. The simplest way to do this is through a data feed contract maintained by a specific party, like NASDAQ, designed so that the party has the ability to update the contract as needed, and providing an interface that allows other contracts to send a message to that contract and get back a response that provides the price. Given that critical ingredient, the hedging contract would look as follows. Wait for party A to input 1,000 Ether, wait for party B to input 1,000 Ether, record the USD value of 1,000 Ether calculated by the querying the data feed contract in storage, say this is $X. After 30 days, allow A or B to reactivate the contract in order to send $X worth of Ether calculated by querying the data feed contract again to get the new price to A and the rest to B. Such a contract would have significant potential in crypto commerce. One of the main problems cited about cryptocurrency is the fact that it's volatile. Although many users and merchants may want the security and convenience of dealing with cryptographic assets, they may not wish to face that prospect of losing 23% of the value of their funds in a single day. Up until now, the most commonly proposed solution has been issuer-backed assets. The idea is that an issue creates a subcurrency in which they have the right to issue and revoke units and provide one unit of the currency to anyone who provides them offline with one unit of a specified underlying asset, which could be like gold or US dollars. The issuer then promises to provide one unit of the underlying asset to anyone who sends back one unit of the crypto asset. This mechanism allows any non-cryptographic asset to be uplifted into a cryptographic asset, provided that the issuer can be trusted. In practice, however, issuers are not always trustworthy. Yes, that's true. And in some cases, the banking infrastructure is too weak or too hostile for such services to exist. Financial derivatives provide an alternative. Here, instead of a single issuer providing the funds to back up an asset, a centralized market of speculators betting that the price of a cryptographic reference asset like Ethereum will go up plays that role. Unlike issuers, speculators have no option to default on their side of the bargain because the hedging contract holds their funds in escrow. Note that this approach is not fully decentralized because a trusted source is still needed to provide the price ticker. Although arguably, even still, this is a massive improvement in terms of reducing infrastructure requirements. Unlike being an issuer, issuing a price feed requires no licenses and can likely be categorized as free speech. Oh yeah, free speech. That's what I'm all about. And reducing the potential for fraud. So you may want to look at the article that I did on gold-backed cryptocurrency, the best of both worlds, potentially. I'll link to that article. Well, I'll link to it on MarketplaceGOLD. You can find it there. And there I talk about the Oris cryptocurrency, which is a cryptocurrency that I'm invested in that is an Ethereum-powered stablecoin. It's one Oris AWG token represents 1 gram of gold. So it's the realization of what is hinted at here in this white paper. Kind of cool, right? Identity and reputation systems. The earliest alternative cryptocurrency of all, which was Namecoin. That's interesting. So Namecoin was the first ever altcoin. Attempted to use a Bitcoin-like blockchain to provide a name registration service where users can register their names in a public database alongside other data. The major cited use case is for a DNS system, mapping domain names like bitcoin.org, or in Namecoin's case, bitcoin.bit to an IP address. Other use cases include email authentication and potentially more advanced reputation systems. Here is the basic contract to provide a Namecoin-like name registration system on Ethereum. The contract is very simple. All it is a database inside the Ethereum network that can be added to, but not modified or removed from. Anyone can register a name with some value, and that registration then sticks forever. A more sophisticated name registration contract will also have a function clause allowing other contracts to query it, as well as a mechanism for the owner, the first registerer of a name, to change the data or transfer ownership. One can even add reputation and web of trust functionality on top. Next, decentralized file storage. Over the past few years, there have emerged a number of popular online file storage startups, the most prominent being Dropbox, which is what I use to share pirated movies. Hey, if you want to be my friend on the internet, I will be a co-pirate along with you, and we can share those movies till the cows come home on Dropbox. I love it. Okay, seeking to allow users to upload a backup of their hard drive and have the service store the backup and allow the user to access it in exchange for a monthly fee. However, at this point, the file storage market is at times relatively inefficient. A cursory look at various existing solutions shows that, particularly at the uncanny valley of 20 to 200 gigabyte level, at which neither free quotas nor enterprise level discounts kick in, monthly prices for mainstream file storage are such that you are paying for more than the cost of the entire hard drive in a single month. I've never thought about that. Ethereum contracts can allow for the development of a decentralized file storage ecosystem where individual users can earn small quantities of money by renting out their own hard drives, and unused space can be used to further drive down the costs of storage. Oh boy, that's kind of a cool idea. I haven't thought of that before. It's kind of like this, the Great Reset thing that you've seen where they say you'll own nothing and you'll be happy somehow. Like basically like you won't own a bed. You'll share a bed. You'll have a decentralized bed. And when you're not sleeping in your bed, like some other dude will be sleeping in your bed. And then hopefully he'll make your bed and and not drool on the pillow by the time that it's time for you to come home and sleep on your bed? So is it going to be kind of like that? Because frankly, I wouldn't be interested in that. Just being honest, just shooting straight with you. Okay, the key underpinning piece of such a device would be what we have termed the decentralized Dropbox contract. This contract works as follows. First, one splits the desired data up into blocks, encrypting each block for privacy, and builds a Merkle tree out of it. One then makes a contract with the rule that every n blocks, the contract would pick a random index in the Merkle tree using the previous hash, accessible from contract code, as a source of randomness, and give X either to the first entity to supply a transaction with a simplified payment verification like proof of ownership of the block at that particular index in the tree. When a user wants to re-download their file, they can use a micropayment channel protocol, which would be something like pay 1 Sabo per 32 kilobytes to recover the file. The most fee-efficient approach is for the payer not to publish the transaction until the end, instead replacing the transaction with a slightly more lucrative one with the same nonce, the number used only once after every 32 kilobytes. An important feature of the protocol is that although it may seem like one is trusting many random nodes not to decide to forget the file, one can reduce the risk down to near zero by splitting the file into many places via secret sharing and watching the contracts to see each piece is still in some node's possession. If a contract is still paying out money, that provides a cryptographic proof that someone out there is still storing the file. Next section, decentralized autonomous organizations. This is the DAO that you've heard so much about. Are you down with the DAO? Well, you'll have all the information you need to decide right here. The general concept of a decentralized autonomous organization is that of a virtual entity that has a certain set number of members or shareholders, which perhaps with a 67% majority have the right to spend the entity's funds and modify its code. The members would collectively decide on how the organization should allocate its funds. Methods for allocating a DAO's funds could range from bounties, salaries, to even more exotic mechanisms, such as an internal currency to reward work. This essentially replicates the legal trappings of a traditional company or nonprofit, but using only cryptographic blockchain technology for enforcement. So far, much of the talk around DAOs has been around the capitalist model of a decentralized autonomous corporation, which would be a DAC, which I think was a character on Star Trek Deep Space Nine, with divided receiving shareholders and tradable shares. An alternative, perhaps described as a decentralized autonomous community, would have all members have an equal share in the decision-making and require 67% of existing members to agree to add or remove a member. The requirement that one person can only have one membership would then need to be enforced collectively by the group. So this is kind of like a country club. You can imagine a country club of a bunch of sophisticated types playing golf, and then someone says, you know what, I want to have Sundays be nudist golf. We're going to be chasing around balls in the nude. And then for him to get his way, he'd have to convince 67% of the other members of the country club. Good luck, buddy. A general outline for how to code a DAO is as follows. The simplest design is simply a piece of self-modifying code that changes if 2/3 of members agree on a change. Although code is theoretically immutable, one can easily get around this and have de facto mutability by having chunks of the code in separate contacts and having the address of which contracts to call stored in the modifiable storage. In a simple implementation of such a DAO contract, there would be 3 transaction types distinguished by the data provided in the transaction. First, to register a proposal with index I to change the address at storage K to value V. Second, to register a vote in favor of proposal 1. And thirdly, to finalize the proposal if enough votes have been made. The contract would then have clauses for each of these. It would maintain a record of all open storage changes, along with a list of who voted for them. It would also have a list of all members. When any storage chain gets to 2/3 of members voting for it, a finalizing transaction could execute the change. A more sophisticated skeleton would also have built-in voting ability for features like sending a transaction, adding members, and removing members, and may even provide for liquid democracy, which is maybe something that goes on in your bedroom. Sometimes it does in mine. Style vote delegation. Anyone can assign someone to vote for them, and assignment is transitive. So if A assigns B and B assigns C and C determines A's vote. This design would allow the DAO to grow organically as a decentralized community, allowing people to eventually delegate the task of filtering out who is a member to specialists. Although, unlike in the current system, specialists can easily pop in and out of existence over time as individual community members change their assignments. An alternative model is for a decentralized corporation, where an account can have 0 or more shares, and 2/3 of the shares are required to make a decision. A complete skeleton would involve asset management functionality, the ability to make an offer to buy or sell shares, and the ability to accept offers, preferably with an order matching mechanism inside the contract. Delegation would also exist, liquid democracy style, generalizing the concept of a board of directors. Further applications. Savings wallets. Suppose that Alice wants to keep her funds, but is worried that she will lose or that someone will hack her private key. She puts Ether into a contract with Bob, a bank, as follows. El Banco de Bob. First, Alice alone can withdraw a maximum of 1% of the funds per day. Bob alone can withdraw a maximum of 1% of the funds per day. But Alice has the ability to make a transaction with her key, shutting off this ability. Alice and Bob together can withdraw anything. Normally, 1% per day is enough for Alice, unless she wants to go on a shopping spree at the Mall of Dubai. And if Alice wants to withdraw more, she can contact Bob for help. If Alice's key gets hacked, she runs to Bob to move the funds to a new contract. Jeez, this is just so patriarchal. Such a problematic white paper. Alice needs to go ask Bob for permission for her funds. I don't know if I'm down with all this. I'm not so sure. We may need to report this for hate speech. Please don't report it for hate speech. It's just a hypothetical. It's just a hypothetical. If she loses her key, Bob will get the funds out eventually. If Bob turns out to be malicious, and I have never known a Bob who is malicious. All Bobs I've known are terribly benign. Then she can turn off his ability to withdraw. Crop insurance for when the grand solar minimum comes for all of us, right? Dun 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 dun. Google that one. That's a rabbit hole to go down. One can easily make a financial derivatives contract by using a data feed of the weather instead of any price index. If a farmer in Iowa purchases a derivative that pays out inversely based on the precipitation in Iowa, then if there is a drought, the farmer will automatically receive money, and if there is enough rain, the farmer will be happy because their crops would do well. This can be expanded to natural disaster insurance generally. Yes, I would like to take out insurance on the 10th planet coming into the solar system and rocking life as we know it. Thirdly, a decentralized data feed. For financial contracts for difference, it may actually be possible to decentralize the data feed via a protocol called shelling coin. Shelling coin basically works as follows. N parties all put into the system the value of a given datum tag, like the Ethereum to USD price. The values are sorted, and everyone between the 25th and 75th percentile gets one token as a reward. Everyone has the incentive to provide the answer that everyone else will provide. And the only value that a large number of players can realistically agree on is the obvious default, the truth. This creates a decentralized protocol that can theoretically provide any number of values, including the Ethereum USD price, the temperature in Berlin, or even the result of a particular hard computation. Fourthly, smart multi-signature escrow. Bitcoin allows multi-signature transaction contracts where, for example, 3 out of a given 5 keys can spend the funds. Ethereum allows for more granularity. For example, 4 out of 5 can spend everything. 3 out of 5 can spend up to 10 per day. And 2 out of 5 can spend up to 0.5 per day. Additionally, Ethereum multisig is asynchronous. 2 parties can register their signatures on the blockchain at different times, and the last signature will automatically send the transaction. 5. Cloud computing. The EVM technology can also be used to create a verifiable computing environment, allowing users to ask others to carry out computations and then optionally ask for proofs that computations at certain randomly selected checkpoints were done correctly. This allows for the creation of a cloud computing market where any user can participate with their desktop, laptop, or specialized server, and spot checking together with security deposits can be used to ensure that the system is trustworthy, that nodes cannot profitably cheat. Although such a system may not be suitable for all tasks that require a high level of inter-process communication, for example, cannot easily be done on a large cloud of nodes. Other tasks, however, are much easier to parallelize. Projects like SETI at home, is that where they're finding the aliens at home when we're scanning for aliens? Folding at home, that sounds less interesting than the search for intelligent life beyond our solar system. And genetic algorithms can easily be implemented on top of such a platform. 6th, peer-to-peer gambling. Oh yes, importantly, when we're doing a world-rocking technological innovation, Gambling. We must let people gamble. We must enable people's gambling. Any number of peer-to-peer gambling protocols, such as Frank Stajano and Richard Clayton's CyberDice, can be implemented on the Ethereum blockchain. The simplest gambling protocol is actually simply a contract for difference on the next block hash, and more advanced protocols can be built up from there, creating gambling services with near zero fees that have no ability to cheat. Well, what is the point of gambling if you can't cheat? Seventh, prediction markets. Provided an oracle or Schelling coin, prediction markets are also easy to implement. And prediction markets together with Schelling coin may prove to be the first mainstream application of futurarchy, which is a cool word. I've never heard it before, but I like it. Futurarchy as a governance protocol for decentralized applications. So this is a super cool idea that I've heard described several other places, where in society, instead of these like corrupt bureaucrats making all sorts of decisions about what we're going to do about, say, I don't know, how a country responds to political turmoil or war or whatever, you would have a betting market, and you would have a bunch of different people betting their own money as to what was going to be the outcome of certain future things happening, and then you would base policy upon that. And because people had skin in the game, you would get like really intelligent, predictive markets, so that bureaucrats and politicians and business people weren't making idiotic decisions that had catastrophic externalities for society. Look into it. That's the future right there. 8. On-chain decentralized marketplaces using the identity and reputation system as a base. So that's all of the people who are buying weed out there in these dark web websites. Don't do that. Say no to drugs, kids. Okay, and we are going to move on now to the miscellanea and concerns section of the story here of the white paper. And I told you in the introduction that there was going to be a silly word that you're going to be listening for. And if you send me that silly word, I'll send you back a bit of crypto. Maybe Ethereum, maybe something else. You'll just have to send me an email or drop me a message anywhere on social media. Again, I'm Jonathan Roseland. I'm an easy guy to find. And the silly word is going to be no pants party. That's right. No pants party. You may say, Jonathan, that's 3 words. Yes, but I want you to send it to me as a single word, because they were mentioning Berlin earlier, and I was just thinking about Berlin. I once spent a few months in Berlin. It was a wild time, and I once went to a no pants party in Berlin. That's right. So send that on over to me. Okay, back to the section here. Miscellanea and concerns. First of all, let's hear about a modified Ghost implementation, which is not a thing on one of those TV shows where they search for ghosts and always manage to find them. The greedy heaviest observed subtree, or ghost. Greediest heaviest observed subtree. That's right, that's an acronym. Never knew it. Protocol is an innovation first introduced by Jonathan Skompolimsky. I have no idea how to say that last name. And Aviz Zohar in December of 2013. The motivation behind Ghost is that blockchains with fast confirmation times currently suffer from reduced security due to a high stale rate, because blocks take a certain time to propagate through the network. If miner A mines a block and then miner B happens to mine another block before miner A blocks propagates to B, miner's B block will end up wasted and will not contribute to network security. Furthermore, there is a centralization issue. If miner A is a mining pool with 30% hash power and B has 10% hash power, A will have a risk of producing a stale block 70% of the time, since the other 30% of the time A produced the last block, and so we'll get the mining data immediately, whereas B will have a risk of producing a stale block 90% of the time. Thus, if the block interval is short enough for the state rate to be high, A will be substantially more efficient simply by virtue of its size. With these two effects combined, blockchains which produce blocks quickly are very likely to lead to one mining pool having a large enough percentage of the network hash power to have de facto control over the mining process, which is not what we want. As described by Sompolinsky and Zohar, Ghost solves the first issue of network security loss by including stale blocks in the calculation of which chain is the longest. That is to say, not just the parent and further ancestors of a block, but also the stale descendants of the block's ancestor. In Ethereum jargon, uncles. So yeah, we've got uncles, we've got ancestors, we've got Alice and Bob, we've got a whole family coming together here, are added to the calculation of which block has the largest total proof of work backing it. To solve the second issue of centralization bias, we go beyond the protocol described by Sompolinsky and Zohar and also provide block rewards to stales. A stale block receives 87.5 of its reward base, and the nephew that includes the stale block receives the remaining 12.5. Transaction fees are not awarded to uncles. The uncles are getting screwed here. Ethereum implements a simplified version of Ghost, which only goes down 7 levels. Specifically, it is defined as follows. A block must specify a parent and it must specify 0 or more uncles. An uncle included in block B must have the following properties. It must be the direct child of the KTH generation ancestor of B, whereas it cannot be an ancestor of B. An uncle must be a valid block header, but does not need to be a previously verified or even valid block. An uncle must be different from all uncles included in previous blocks and all other uncles included in the same block. Non-double inclusion. For every uncle in block B, the miner of B gets an additional 3.125% added to its Coinbase reward. Coinbase? When did Coinbase get involved with all this? And the miner of U gets 93.75 of a standard Coinbase reward. This limited version of Ghost with uncles includable only up to 7 generations was used for 2 reasons. First, unlimited Ghost would include too many complications into the calculation of which uncles for a given block are valid. Second, unlimited Ghost with compensation as used in Ethereum removes the incentive for a miner to mine on the main chain and not the chain of a public attacker. Moving on, fees. Because every transaction published into the blockchain imposes on the network the cost of needing to download and verify it, there is a need for some regulatory mechanism, typically involving transaction fees to prevent abuse. The default approach used in Bitcoin is to have purely voluntary fees, relying on miners to act as the gatekeepers and set dynamic minimums. This approach has been received very favorably in the Bitcoin community, particularly because it is market-based, allowing supply and demand between miners and transaction centers to determine the price. The problem with this line of reasoning is, however, that transaction processing is not a market. Although it is intuitively attractive to construe transaction processing as a service that the miner is offering to the sender. In reality, every transaction that a miner includes will need to be processed by every node in the network. So the vast majority of the cost of transaction processing is borne by third parties, and not the miner that is making the decision of whether to include it. Hence, tragedy of the commons problems are likely to occur. And tragedy of the commons is like when you have a group of roommates living together in a flat and nobody ever cleans up in the kitchen. Everybody just leaves a mess in the kitchen, and then you get in arguments. That is a tragedy in the commons that I have experienced myself. However, as it turns out, this flaw in the market-based mechanism, when given a particular inaccurate simplifying assumption, magically cancels itself out. The argument is as follows. Suppose that 1, a transaction leads to K operations, offering the reward KR to any miner that includes it where R is set by the sender and K and R are roughly visible to the miner beforehand. 2, a operation has a processing cost of C to any node. All nodes have equal efficiency. There are n mining nodes, each with exactly equal processing power. And 4, no non-mining full nodes exist. A miner would be willing to process a transaction if the expected reward is greater than the cost. Thus, the expected reward is KRN, since the miner has 1n chance of processing the next block, and the processing cost of the miner is simply KC. Hence, miners will include transactions where ... Note that R is the per operation fee provided by the sender and is thus a lower bound on the benefit that the sender derives from the transaction. And NC is the cost to the entire network together of processing an operation. Hence, miners have the incentive to include only those transactions for which the total utilitarian benefit exceeds the cost. However, there are several important deviations from these assumptions in reality. 1, miner does pay a higher cost to process the transaction than the other verifying nodes, since the extra verification time delays block propagation and thus increases the chance the block will become stale. There do not exist non-mining full nodes. And 3, the mining power distribution may end up radically inegalitarian in practice. Boy, things tend to end up radically inegalitarian in practice. Isn't that something that just kind of generalizes to the world? Speculators, political enemies, my political enemy is my wife's dog, and crazies whose utility function includes causing harm to the network do exist, and they can cleverly set up contracts where their cost is much lower than the cost being paid by other verifying nodes. 1 provides a tendency for the miner to include fewer transactions, and 2, increase NC. Hence, these 2 effects at least partially cancel each other out. 3 and 4 are the major issue. To solve them, we simply institute a floating cap, which means that no block can have more operations than block limit factor times the long-term exponential moving storage. And then there's a piece of computer code. block limit factor and MF factor are constants that will be set to 65536 and 1.5 for the time being, but they will likely be changed after further analysis. There is another factor disincentivizing large block sizes in Bitcoin. Blocks that are large will take longer to propagate and thus have a higher probability of becoming stales. In Ethereum, highly gas-consuming blocks can also take longer to propagate, both because they are physically larger and because they take longer to process the transaction stale transitions to validate. This delay disincentive is a significant consideration in Bitcoin, but less so in Ethereum because of the Ghost protocol. Hence, relying on regulated block limits provides a more stable baseline. Next, we're going to talk about computation and Turing completeness. Oh yes, Turing completeness. This is what gives crypto bros raging erections, doesn't it, gents? An important note is that the Ethereum virtual machine is Turing complete. This means that EVM code can encode any computation that can be conceivably carried out, including infinite loops. EVM code allows looping in two ways. First, there is a jump instruction that allows the program to jump back to a previous spot in the code. And a jumpy instruction can do conditional jumping, allowing for statements like while x27 equals da da da. Second, contracts can call other contracts, potentially allowing for looping through recursion. This naturally leads to a problem. Can malicious users essentially shut miners and full nodes down by forcing them to enter into an infinite loop? The issue arises because of a problem in computer science known as the halting problem. There is no way to tell in the general case whether or not a given program will ever halt. That's right, human beings, we halt on our own. We don't need we go so far and then we halt, but our silicone friends are a different story. As described in the state transition section, our solution works by requiring a transaction to set a maximum number of computational steps that it is allowed to take. And if execution takes longer, computation is reverted, but fees are still paid. Messages work in the same way. To show the motivation behind our solution, consider the following examples. An attacker creates a infinite loop and then sends a transaction activating that loop to the miner. The miner will process the transaction running the infinite loop and wait for it to run out of gas. Even though the execution runs out of gas and stops halfway through, the transaction is still valid, and the miner still claims the fee from the attacker for each computational step. Next, an attacker creates a very long infinite loop with the intent of forcing the miner to keep computing for such a long time that by the time computation finishes, a few more blocks will have come out, and it will not be possible for the miner to include the transaction to claim the fee. However, the attacker will be required to submit a value for start gas, limiting the number of computational steps that execution can take, so the miner will know ahead of time that the computation will take an excessively large number of steps. Also, an attacker sees a contract with code for some form like send a contract storage A equals 0, and sends a transaction with just enough gas to run the first step but not the second. For example, making a withdrawal but not letting the balance go down. The contract author does not need to worry about protecting against such attacks because if execution stops halfway through the changes, they get reverted. A financial contract works by taking the median of 9 proprietary data feeds in order to minimize risk. An attacker takes over one of the data feeds, which is designed to be modifiable via the variable address call mechanism described in the section on DAOs, and converts it to run an infinite loop, thereby attempting to force any attempt to claim funds from the financial contracts to run out of gas. However, the financial contract can set a gas limit on the message to prevent this problem. The alternative to Turing completeness is Turing incompleteness, where jump and jump E do not exist, and only one copy of each contract is allowed to exist in the call stack at any given time. With this system, the fee system described and the uncertainties around the effectiveness of our solution might not be necessary, as the cost of executing a contract would be bounded above by its size. Additionally, Turing incompleteness is not even that big of a limitation. Out of all the contract examples we have conceived internally, so far, only one required a loop. And even that loop could be removed by making 26 repetitions of a one-line piece of code. Given the serious implications of Turing completeness and the limited benefit, why not simply have a Turing incomplete language? In reality, however, Turing incompleteness is far from a neat solution to the problem. To see why, consider the following contracts. And we've got some computer code. Now, send a transaction to A. Thus, in 51 transactions, we have a contract that takes up 2 to the 50th power computational steps. Miners could try to detect such logic bombs ahead of time by maintaining a value alongside each contract specifying the maximum number of computational steps that it can take, and calculating this for contracts calling other contracts recursively. But that would require miners to forbid contracts that create other contracts, since the creation and execution of all 26 contracts above could easily be rolled into a single contract. Another problematic point is that the address field of a message is a variable. So in general, it may not even be possible to tell which contracts a given contract will call ahead of time. Hence, all in all, we have a surprising conclusion. Turing completeness is surprisingly easy to manage, and the lack of Turing completeness is equally surprisingly difficult to manage unless the exact same controls are in place. But in the case, why not just let the protocol be Turing complete? Okay, I think I'm hearing ya. Next, currency and issuance. The Ethereum network includes its own built-in currency, Ether, which serves the dual purpose of providing a primary liquidity layer to allow for efficient exchange between various types of digital assets, and more importantly, of providing a mechanism for paying transaction fees. For convenience and to avoid future argument, see the current MBTC, UBTC, Satoshi debate in Bitcoin. The denominations will be pre-labeled 1 Wei, 2 Szabo, 3 Finny, and 4 Ether. This should be taken as an expanded version of the concept of dollars and cents, or BTC and Satoshi. In the near future, we expect Ether to be used for ordinary transactions, Finny for microtransactions, and Szabo and Wei for technical discussions around fees and protocol implementation. The remaining denominations may become useful later, and should not be included in clients at this point. The issuance model will be as follows. Ether will be released in a currency sale at a price of 1,000 to 2,000 Ether per BTC, a mechanism intended to fund the Ethereum organization and pay for development that has been used with success by other platforms such as Mastercoin and NXT. Earlier buyers will benefit from larger discounts. The BTC received from the sale will be used entirely to pay salaries and bounties to developers and invested into various for-profit and non-profit projects in the Ethereum and cryptocurrency ecosystem. 0.099x of the total amount sold, which will be 60 million Ethereum, will be allocated to the organization to compensate early contributors and pay ETH-denominated expenses before the Genesis block. 0.099x, the total amount sold, will be maintained as a long-term reserve. 0.26x, the total amount sold, will be allocated to miners per year forever after that point. Group at launch after 1 year and after 5 years. Okay, and then currency units, and the purchases reserve spent pre-sale 8.26 reserves. So we'll look at the long-term supply growth percent, the long-term inflation rate. Despite the linear currency issuance, just like with Bitcoin, over time, the supply growth rate nevertheless tends towards zero. The two main choices in the above model are, one, the existence and size of an endowment pool, and two, the existence of a permanently growing linear supply, as opposed to a capped supply as in Bitcoin. The justification of the endowment pool is as follows. If the endowment pool did not exist and the linear issuance reduced to 0.27x to provide the same inflation rate, then the total quality of Ether would be 16.5 less, and so each unit would be 19.8% more valuable. Hence, in the equilibrium of 19.8, more Ether would be purchased in the sale. So each unit would once again be exactly as valuable as others, as before. The organization would also then have 1.198x as much BTC, which can be considered to be split into two slices, the original BTC and the additional 0.198x. Hence, this situation is exactly equivalent to the endowment, but with one important difference. The organization holds purely BTC, and so is not incentivized to support the value of the Ether unit. The permanent linear supply growth model reduces the risk of what some see as excessive wealth concentration in Bitcoin. Oh, excessive wealth concentration risk. There's no risk there. I laugh from the deck of my yacht as I do cocaine. Anyways, and gives individuals living in the present and future eras a fair chance to acquire currency units, while at the same time retaining a strong incentive to obtain and hold Ether, because the supply growth rate as a percentage still tends to zero over time. We also theorize that because coins are lost over time due to carelessness, death, pets, eating into cords of computers and electrocuting themselves, tragically resulting in the loss of coins. We'll have to say a prayer. We'll have to say a prayer to, our coins that are lost. May they rest in peace in a better place beyond this world when they're gone. And coin loss can be modeled as a percentage of total supply per year. that the total currency supply in circulation will in fact eventually stabilize at a value equal to the annual issuance divided by the loss rate. For example, at a loss rate of 1%, once the supply reaches 26x, then 0.26x will be mined and 0.26x lost each year, creating an equilibrium, just like with that movie with that one guy that had a great six-pack. What was the name of that movie? Equilibrium. Right, yeah, of course. Anyways, note that in the future, it is likely that Ethereum will switch to a proof-of-stake model for security, reducing the issuance requirements to somewhere between 0 and 0.05x per year in the event that the Ethereum organization loses funding or for any other reason disappears. We leave open a social contract. Anyone has the right to create a future candidate version of Ethereum, with the only condition being that the quantity of Ether must be equal to some calculations, where n is the number of years after the Genesis block. Creators are free to crowd sell or otherwise assign some or all of the difference between the POS-driven supply expansion and the maximum allowable supply expansion to pay for development. Candidate upgrades that do not comply with the social contract may justifiably be forked into compliant versions. And yes, if you're a candidate for anything and you don't comply with the social contract, you should be forked and staked. Moving on, let's talk about mining centralization. The Bitcoin mining algorithm works by having miners computate SHA-256 on slightly modified versions of the block header millions of times over and over again, until eventually one node comes up with a version whose hash is less than the target, currently around 2 to the 192nd power. However, this mining algorithm is vulnerable to two forms of centralization. First, the mining ecosystem has come to be dominated by ASICs, application-specific integrated circuits, computer chips designed for and therefore thousands of times more efficient at the task of Bitcoin mining. This means that Bitcoin mining is no longer a highly centralized and egalitarian pursuit, requiring millions of dollars of capital to effectively participate in. Second, most Bitcoin miners do not actually perform block validation locally. Instead, they rely on a centralized mining pool to provide the block headers. This problem is arguably worse. As of the time of this writing, the top 3 mining pools indirectly control roughly 50% of processing power in the Bitcoin network. Although this is mitigated by the fact that miners can switch to other mining pools if a pool or a coalition attempts a 51% attack. We don't want that, do we? 51% attacks is what a Bitcoiner's nightmares are made of. The current intent at Ethereum is to use a mining algorithm where miners are required to fetch random data from the state, computate some random selected transactions from the last n blocks in the blockchain, and return the hash of the result. This has 2 important benefits. First, Ethereum contracts can include any kind of computation. So an Ethereum ASIC would essentially be an ASIC for general computation. For example, a better CPU. Second, mining requires access to the entire blockchain, forcing miners to store the entire blockchain and at least be capable of verifying every transaction. This removes the need for centralized mining pools, although mining pools can still serve the legitimate role of evening out the randomness of reward distribution. This function can be served equally well by peer-to-peer pools with no central control. This model is untested, and there may be difficulties along the way in avoiding certain clever optimizations when using contract execution as a mining algorithm. However, one notably interesting feature of this algorithm is that it allows anyone to poison the well by introducing a large number of contracts into the blockchain specifically designed to stymie certain ASICs. The economic incentives exist for ASIC manufacturers to use such a trick to attack each other. Thus, the solution that we are developing is ultimately an adaptive economic human solution rather than a purely technical one. And there you hear it again. Successful cryptocurrencies account for human nature. Moving on, we'll talk about scalability. One common concern about Ethereum is the issue of scalability. Like Bitcoin, Ethereum suffers from the flaw that every transaction needs to be processed by every node in the network. With Bitcoin, the size of the current blockchain rests at about 15 gigabytes, growing by about 1 megabyte per hour. If the Bitcoin network were to process Visa's 2,000 transactions per second, wow, it would grow by 1 megabyte per 3 seconds, or 1 gigabyte per hour, which comes out to 8 terabytes per year. Ethereum is likely to suffer a similar growth pattern, worsened by the fact that there will be many applications on top of the Ethereum blockchain instead of just a currency, as is the case with Bitcoin, but ameliorated by the fact that Ethereum full nodes need to store just the state instead of the entire blockchain history. The problem with such a large blockchain size is centralized risk. If the blockchain size increases to, say, 100 terabytes, then the likely scenario would be that only a very small number of large businesses would run full nodes, with all regular users using light SPV nodes. In such a situation, there arises the potential concern that the full nodes could band together and all agree to cheat in some profitable fashion, because people are always agreeing to cheat in a profitable fashion, like changing the block reward, giving themselves BTC. Light nodes would have no way of detecting this immediately. Of course, at least one honest full node would likely exist, and after a few hours, information about the fraud would trickle out through channels like Reddit. But at that point, it would be too late. It would be up to the ordinary users to organize an effort to blacklist the given blocks. A massive and likely unfeasible coordination problem on a similar scale as that of pulling off a successful 51% attack. So imagining this would be something like if you had an evil pet shop owner and all the kittens in the pet shop organized together to revolt against the pet shop owner. We're talking about the same sort of likelihood here. In the case of Bitcoin, this is currently a problem, but there exists a blockchain modification suggested by Peter Todd, which will alleviate this issue. Bravo, Peter. In the near term, Ethereum will use two additional strategies to cope with this problem. First, because of the blockchain-based mining algorithm, at least every miner will be forced to be a full node, creating a lower bound on the number of full nodes. Second, and more importantly, however, we will include an intermediate state tree root in the blockchain after processing each transaction. If the block validation is centralized, as long as one honest verifying node exists, the centralization problem can be circumvented via a verification protocol. If a miner publishes an invalid block, that the block must either be badly formatted or the state is incorrect. Since S0 is known to be correct, there must be some first state, SI, that is incorrect, where SI1 is correct. The verifying node would provide the index I along with proof of invalidity consisting of the subset of Patricia tree nodes needed to process apply S1I TXI equals SI. Nodes would be able to use those Patricia nodes to run that part of the computation and see that the SI generated does not match the SI provided. Another more sophisticated attack would involve the malicious miners publishing incomplete blocks so the full information does not even exist to determine whether or not blocks are valid. The solution to this is a challenge response protocol. Verification nodes issue challenges in the form of target transaction indices, and upon receiving a light node treats the block as untrusted until another node, whether the miner or another verifier, provides a subset of Patricia nodes as a proof of validity. Whew! I think I've got a solution for this whole situation here with the invalid attackers, the invalid miners, with all the shenanigans that people are trying to pull. My solution is going to be block dueling. We're going to have D coin for dueling, and we're going to go back in time. We're going to go old school. And if you think that someone is pulling some shenanigans on the blockchain, you're just going to be able to challenge them to a duel, either with pistols in a field or with swords. And you can either duel to the death or duel to first blood. And you call a man out for being a cheater and a coward, and he'll say, "Oh, I'll duel you for it." And then one of you guys has to go in a field, dress in those frou-frou, those fancy shirts that guys used to wear when they were dueling, and go out there and settle it like gentlemen. I think that might resolve all of these kind of issues. But unfortunately, that is not possible. So I'm thankful that we have this antifragile system developed by Vitaly Buterin and co. Okay, here's the conclusion of the white paper. The Ethereum protocol was originally conceived as an upgraded version of a cryptocurrency, providing advanced features such as on-blockchain escrow, withdrawal limits, financial contracts, gambling markets, and the like via a highly generalized programming language. The Ethereum protocol would not support any of the applications directly, but the existence of a Turing-complete programming language means that arbitrary contracts could theoretically be created for any transaction type or application. What is more interesting about Ethereum, however, is that the Ethereum protocol moves far beyond just currency. Protocols around decentralized file storage, decentralized computation, and decentralized prediction markets, among dozens of other concepts, have the potential to substantially increase the efficiency of the computational industry and provide a massive boost to other peer-to-peer protocols by adding, for the first time, an economic layer. Finally, there is also a substantial array of applications that have nothing to do with money at all. The concept of an arbitrary state transition function, as implemented by the Ethereum protocol, provides for a platform with unique potential, rather than being a closed-ended single-purpose protocol intended for a specific array of applications in data storage, gambling, or finance. Ethereum is open-ended by design. And we believe that it is extremely well suited to be serving as a foundational layer for a very large number of both financial and non-financial protocols in the years to come. And that is the Ethereum Whitepaper. We have got through it together. So I am debating with myself whether it was worth it for me to read this. I am going to be investing in Ethereum shortly myself, and I wanted to know what I was buying. So I took the time to read this. It's notable that Ethereum, I think the assumptions, the predictions that were made in this paper back in 2013 have proved themselves. Ethereum has become the second most popular cryptocurrency in existence. It remains an innovative, visionary advance in computer science, in economics, and I'm excited to see the way that it develops. I'm excited to see the things that people continue to build on top of it. Again, I'm Jonathan with Marketplace Gold. And if you have some sort of business, if you have an organization, if you're a freelancer, and you accept Ethereum for payment, I think you're very wise, because I think Ethereum has tremendous upside to grow in value, grow in popularity as time goes on. And you can list yourself, list your business on MarketplaceGOLD.com. I have got links below wherever you're listening to this to do so. And I look forward to a continued conversation with you.